Hi class, welcome back to multivariable calculus. This is our final lecture of the semester and we are going to be focusing on Green's theorem. So recall last class when we were testing for path dependence and whether or not a certain field, vector field, was a gradient vector field. So in other words, conservative. And in order to do that, we took the partial derivative of our x component of the field with respect to y and the partial derivative of our y component of the field with respect to x. If the two were equal, then we had a gradient field, meaning it has a potential function and it's conservative. So now let's take a look at Green's theorem. So let's rewrite what I just said in a more formal way. So say we have an integral over some region of del f2 over del x minus del f1 over del y dx dy. Well, when this is 0, right, but if the two inner pieces are 0, right, then this is going to be, the whole thing is going to be 0. This is 0 when vector f is a gradient field for every conservative field where we have the line integral of f dot dr, in other words, the work is 0. So let's think a little bit about why. So there exists a potential function such that the vector field is equal to the gradient of that potential function. So it's a gradient vector field. So that means that our x component, f sub 1 of our field, is equal to our partial derivative of our potential with respect to x, and f2, the y component of our field, is equal to the partial derivative of our potential function with respect to y. So in that case, del f2 over del x is equal to f sub y x. So that's the second order mixed partial, and we used this a couple of classes ago to check for path independence. And also del f1 over del y is then equal to this second order mixed partial, f sub xy. So then, since we know that f sub yx has to equal f sub xy, then del f2 over del x is equal to del f1 over del y. So of course, del f2 over del x minus del f1 over del y would of course be 0. All right, and so that gives us integral of the region of del f2 over del x minus del f1 over del y dx dy is going to be equal to the integral of 0 dx dy, which is 0. And one more thing to note, this piece in here This is known as the scalar curl. The definition of it. So now let's move on to our first exercise. And let's suppose C is a closed curve. And without using Green's theorem, we're going to show the line integral along C is 0 when the vector field is a gradient field. And so remember, we want to show that the line integral of f dot dr is going to be 0 when f is a gradient field. So now let's start. We're going to draw any closed oriented curve C and break it into two parts, C sub 1 and C sub 2, by labeling the endpoints and marking a direction for C1 and C2. So let's draw some curve. And I am going to say, let's say this is A, point A, and this is point B. And so I'm going to say that C1 goes in this counterclockwise direction from B to A. And I'm going to say C2 is also going to go from A to B. All right, and be this line, this curve segment. So we're going to write an equation for the line integral in terms of C sub 1 and C sub 2. Okay, so this first curve and the second curve. And then use the fundamental theorem of line integrals to deduce that the line integral along C is 0. So let us start with, so we have the line integral of f dot dr is going to be equal to the line integral from C over C1, so from B to A, of f dot dr plus, so if we say C is the entirety of C1 plus C2, line integral C2 f dot dr. All right. So this is going to be if we use the fundamental theorem of line integrals. So we're going to say that this is a gradient field, so there exists some potential function f. So the potential function evaluated at point B minus the potential function evaluated at A. Okay, so fb minus fa gives us this first line integral using the fundamental theorem of line integrals. And then we're going to add on to it, we're going to evaluate at our endpoint for our second one, which is going to be A. 1 second. All right, sorry about that. I was going crazy there for a second. So, wait, that's not going to work. All right, so our C sub 1 starts at B and ends at A, so we know it's ending minus beginning, plus f of B, which is the ending point for C2, minus f of A. And so the FAs are going to cancel, the F of B's are going to cancel, and we end up with 0. Okay, so we have shown it. Okay, next. We're going to evaluate the line integral without using Green's theorem. So I'm going to give you a line integral. So we're going to look for f dot dr, the line integral. And we're going to have f of x and y. So our vector field is going to be x to the 4th I hat plus x, y, j hat. And C is going to be the triangle And C is the triangle connecting the points 0, 0, 1, 0, and 0, 1, oriented counterclockwise. Okay, so using then that f dot dr is going to be the integral from a to b of f rt dotted with r prime t dt, just like we were doing several lectures ago. And so let's just start by drawing out our triangle. And we're going to go mark point, this will be 1, 0, 0, 1, 0, 0. And let's go C1 and C2 and C3. Okay, so there's our curve. So now we need to come up with a series of parameterizations for our position vector, since we are doing this in 3 parts. So we're going to have a piecewise function. So our position vector, r of t, so we have to describe it going from 0, 0, 1, 0 to 0, 1 using some time interval. So to get from 0, 0 to 1, 0, we could say we're going t I hat, because we're only moving in the x direction. And we can set that as 0 is less than or equal to t is less than or equal to 1. And then for our next piece, we're going from 1, 0 to 0, 1. And I'm going to make it so that occurs over the next second or next time interval. So we can do 2 minus t I hat plus t minus 1 j hat, and that'll be for 1 is less than or equal to t is less than or equal to 2. And so we can also check this. So go ahead and double check, plug in 1 for t, and of course we get 2 minus t is 1, and then plug in 1 for t here, we get 0, so that's our 1, 0. And then if we plug in 2, we get 2 minus 2 is 0. And we get 2 minus 1 is 1. Okay, so we're going from 1, 0 to 0, 1. That works out well. Then for our next one, I'm going to go from time 2 to 3. So that's going to give us, we want to get back to 0, 0. And so we can do 3 minus t j hat, and that'll be from 2 to 3. All right, so now that is the parameterization of our curve. And so now we have to go and take the derivative there, all right, with respect to t. And we end up with I hat for 0 is less than or equal to t is less than or equal to 1. Then we get minus I hat plus j hat for 1 is less than or equal to t is less than or equal to 2. And then we get minus j hat for 2 is less than or equal to t is less than or equal to 3. All right, so as you can see, it's already taken quite a bit of work to set this up, doing it following this method. So now we need to go ahead and write out our field f as a function of time. And so we can write f of r of t is going to be t to the fourth I hat for 0 is less than or equal to t is less than or equal to 1. And then we have 2 minus t here is going to be our x to the fourth I hat plus 2 minus t, so our x, y, j hat, so x is 2 minus t, y is t minus 1, j hat, okay, and that's going to be from 1 to 2. And then our last piece is just going to be, well, that one turns out pretty nice because it's just going to be minus j hat. And in that case, minus j hat is going to be 0. All right. And if there's no t, okay, I glanced at the wrong thing for a sec. So here, our y component is 3 minus t, so y is 3 minus t, but our I hat component, our x component is 0, so 0 times 3 minus t is 0, so we have 0 here from 2 to 3. All right, now we got to keep going. I don't know why that got so tiny. Don't worry about it. All right, so we're going to exercise 36.2, continued. Okay, so now let's go ahead and compute our line integral. So the line integral of f dot dr is going to be equal to the line integral from 0 to 1. So that, remember, that's our time interval, 0 to 1 for our first part. And then we just plug in t to the fourth I hat. And we're going to dot that with r prime of t, which was I hat, dt, plus our next time interval, which was from 1 to 2. And there we're going to have 2 minus t to the fourth I hat plus 2 minus t times t minus 1 j hat dotted with minus I hat plus j hat dt plus our last piece, which is going to go from 2 to 3, and that's going to be 0, so I don't even need to write that in. Okay, so this is going to give us integral from 0 to 1 of t to the fourth dt plus the integral from 1 to 2 of minus 2 minus t to the fourth plus 3t minus 2 minus t squared dt, which is going to give us, well, this first piece here, integrate t to the fourth dt, is going to give us t to the fifth, t to the fifth over 5, and that's going from 0 to 1, plus 3t squared over 2 minus 2t minus t cubed over 3, and that's going to be from 1 to 2. All right, so now for this part, we're going to have to do a u substitution. Okay, so for this part, we're going to have to do a u substitution. So let's let u equal 2 minus t, and then oh, I didn't write down the last piece. All right, let's write down the last piece. We can split this into two. So this piece is pretty easy to integrate, but so that was this part right here, but this part, the minus 2 to the fourth, is more challenging. So we will definitely include that and write it down. So we got 1 to 2 of minus 2 minus t to the fourth dt. Now we can do our u substitution. So we're going to let u equal 2 minus t. So du is going to equal minus dt. And so we get then this first one is 1/5 plus we have 6 minus 4 minus 8/3 if we plug in 2. And then we want to subtract off plugging in 1. So that's going to give us 3/2 minus 2 minus 1/3 plus 2 minus t to the fifth over 5 from 1 to 2. Okay, once we do our u sub. And so we end up with 1/5 plus a bunch of stuff, which ends up being 3 over 6, plus minus 1 over 5, which is going to give us 6 plus 5 minus 6 over 30, which comes out to 5 over 30, which is 1/6. Phew! So we finally got there. So you can see that's a bit of a laborious method. So now let's try to evaluate the same line integral using Green's theorem. Okay. So we have then the integral, the line integral of f dot dr is going to equal the integral over r of del f2 over del x plus del f1 over del y dx dy. And so Green's theorem only works if we have a path dependent vector field, so not a gradient vector field. Because remember, if we have a conservative or a gradient vector field, we know that this line integral comes out to 0, or that the integral over the region of del f2 over del x plus del f1 over del y comes out to 0. So this only works on path dependent line integrals. Okay. So now what we need to do is let's so we don't need to find the parametric equation. So we don't need to find the parametric form of our position vector this time. So let's just look once again at what we had. So we had, look at our curve. So now we're not parameterizing with time. All right, so now we're going to find an equation. So representing this right here, which was is going to be y equals 1 minus x, or x equals 1 minus y. Okay, and so let's take a look. Let's say that del f2, let's rewrite our let's rewrite f just to make this clear. So f is going to be x to the fourth I hat plus x, y, j hat. All right, so now let's look at del f2 over del x first. So del f2 over del x. So looking at this piece with respect to y, with respect to x, del f2 over del x, it's going to give us y. And del f1 over del y, then, there's no y in there, that's going to give us 0. And so that tells us that we're going to have the double integral, because we have to set up a region here, and we have two variables, so we're going to have two integrals. And I'm just noticing my recording screen's looking weird. Hold on a sec. Okay. No, I guess that's fine. All right. So now we have to set up the extents, limits of our integration. So as far as x is concerned, let's integrate from 0 to 1. So we're trying to set up bounds for our region. 0 to 1. And then let's set up the bounds for y in terms of x. So y is going from 0 to 1 minus x. And then we're going to integrate this, and del f1 over del y is 0, so it's just going to be y dy dx. And so this is going to be then the integral from 0 to 1 of, now with respect to y squared over 2, and we're going to go from 0 to 1 minus x, and we still have our dx. And so this is going to become the integral of 1 minus x squared over 2 from 0 to 1 dx, which is going to equal the integral from 0 to 1 of 1/2 minus x plus x squared over 2 dx. And that is going to give us then x over 2 minus x squared over 2 plus x cubed over 6. And we're going to go from 0 to 1. And so we get 1/2 minus 1/2 plus a 6th, which is a 6th. So we have got the exact same answer as last time, so just doing this a different way using Green's theorem, and it's just a much more efficient process. Really, the hardest part here is trying to set up the region of integration, all right? And so you remember for the outer term, so with respect to x, we can set the actual limits here in terms of the coordinates, and then for the inner term, we're going to set y with respect to x. All right, now let's keep going. You're going to try this one on your own, and so you are going to use Green's theorem to find the integral that I am about to give you, and that is going to be for the vector field f is equal to 2x cubed y I hat plus sine x j hat. And we're going to look for the line integral going counterclockwise around C, which is going to be the triangle formed by the points 0, 0, 2, 0, and 0, 4. Okay, so give it a pause, try this one on your own first, and then proceed for the solution. Now looking at this, let's draw out our region. So this will be 2, This will be 4. It's going to be 0, 0, 2, 0, 0, 4. Okay, and we're going counterclockwise, and we have y versus x. All right. And so counterclockwise just gives us the order of, so going counterclockwise, we do del f2 over del x minus del f1 over del y. Going the other direction clockwise would be the reverse. So now let's just write y in terms of x here. So y is going to be 4 minus 2x to set our bound. And so del f2 over del x minus del f1 over del y is going to give us, so del f2 over del x is going to be cosine x, and del f1 over del y is going to be minus, so we have our minus here, and it's going to be 2x cubed. And so our line integral, f dot dr over c, is going to equal the integral of the region of cosine x minus 2x cubed dx dy. So this is going to be, for x, or for y, we're going from 0 to 4. For x, we're going to be going from, we're going to have x equals 2 minus y over 2. Just solving for x there. And so we're going to go from 0 to 2 minus y over 2. And we have cosine x minus 2x cubed dx dy. And so we end up getting the integral from 0 to 4 of sine x minus x to the 4th over 2. And we're going to look at that from 0 to 2 minus y over 2. We still have our dy. And so this is going to give us the integral from 0 to 4. Sure, that looks like a 4. Of sine 2 minus y over 2 minus 2 minus y to the 4th over 2 dy. So we're going to have to do a u sub in here. All right, so let's open up a new sheet to do that. Actually, I'll write it down here. So we're going to let u equal 2 minus y over 2, and du is going to be minus 1/2 dy. All right, so now let's keep going in a new sheet. All right, so now we're going to have the integral of sine u minus u to the 4th over 2 times minus 2 du, okay, because solving for y, dy is 1/2 is minus 2 du. Okay, and this is going to give us integral of u to the fourth minus 2 sine u, just distributing the minus 2, du, which is going to be u to the fifth over 5 plus 2 cosine u, which is going to give us 2 minus y over 2, plugging in for our u, over 5 to the fifth, plus 2 cosine 2 minus y over 2, going from 0 to 4. And so plugging in, or evaluating, we get 0 plus 2 minus 32 over 5 plus 2 cosine 2, which is going to give us minus 2 cosine 2 minus 22 over 5. Okay, so that is it with that one. And let's do one more once again. You may definitely try it on your own if you'd like. So for this one, let's let our field be minus y over x squared plus y squared I hat plus x over x squared plus y squared j hat. And C is going to be the unit circle oriented counterclockwise. Okay, so first, I'd like us to calculate the line integral. So we're going to calculate the line integral using our definition of using parameterization. So we're going to go from a to b of f as a function of position with time, dotted with r prime of t dt. So we're going to first do it that way and then use Green's theorem. So let's start with our parameterization. So r of t is going to be, there are a few different ways you can do this, but I'm going to do cosine t I hat plus sine t j hat, and we're going to go from 0 to 2 pi, going around once. And so r prime of t is going to be minus sine t I hat plus cosine t j hat. And our field written as a function of r of t is going to be, well, our x is minus sine t, our y is cosine t, and so we have minus cosine t divided by sine squared t plus cosine squared t, so this is just going to be minus sine t over 1. And then for our next piece, it's going to be pretty much the same thing, but with sine t, with cosine t on, with, we're looking at the derivative again. Our x is cosine t, our y is sine t, so our x is going to be cosine t over 1. There we go. And so then, let's evaluate our line integral. So we're going to go from 0 to 2 pi, that's our time interval, of minus sine t I hat plus cosine tj hat, I'm using the I hat and j hat here, dotted with minus sine t I hat So the derivative plus cosine t j hat dt. And so we go from 0 to 2 pi then of sine squared t plus cosine squared t. Well, that works out pretty nicely. So it's just going to be the integral from 0 to 2 pi dt, which is just going to be t from 0 to 2 pi, which is just going to be 2 pi. Okay, so now let's try to do this using Green's theorem. So for B, Green's, so remember, it's the integral of the region now of del f2 over del x minus del f1 over del y dx dy. All right, so we get del f2 over del x minus del f1 over del y. So this is, I think, maybe a little more challenging. But we have 1 over x squared plus y squared. Actually, I'm going to write it on top so that you can see what's going on here. Remember, f is going to be minus y over x squared plus y squared I hat plus x over x squared plus y squared j hat. Okay, so we're just taking the partial derivative here of our y component with respect to x. So we're going to get 1 over x squared plus y squared minus 2x squared over x squared plus y squared squared. Okay, and then we're going to subtract off del f1 over del y, which is going to be minus 1 over x squared plus y squared plus 2y squared over x squared plus y squared squared. And so here, trying to simplify a little bit, we get x squared plus y squared. And we're just, what I'm doing is I'm just going to try to get a common denominator of x squared plus y squared squared. So we're just putting everything over one denominator. So I'm multiplying 1 by x squared plus y squared. And then the minus 2x remains the same, minus 2x squared. And then this minus 1 is still going to be minus a minus, so plus x squared plus y squared. And then distribute the minus, we're going to get minus 2y squared. And this is all over x squared plus y squared squared. And so the integral over the region then is going to be del f2 over del x minus del f1 over del y dx dy. Well, all right, so let's take a closer look at this. We have x squared plus x squared is 2x squared, and we're subtracting off a 2x squared. Y squared plus y squared is 2y squared, and we're subtracting off a 2y squared. So this is 0. What happened? Now, I'd like you to think about what happened. Are the two integrals equal? Should they be equal? Why or why not? So what do you think? Think about it a little bit. So ultimately, no, they're not equal because the domain of f, you may notice, has a hole at 0, 0. We cannot have 0 in the denominator. So that is contained in R. So for this, Green's theorem does not apply. So you got to be careful of that. Okay, so it's a special case when there's a hole in the denominator or a hole in the domain, you cannot apply Green's theorem. So you got to check for discontinuities. All right. Well, that is it. That is the end of our final calculus lecture. And so after this, you just have a couple assignments. Well, you have the homework and the final. And so I'll be in touch via Moodle. And let me know if you have any questions. Take care. Happy studying.